So let's take a look at an example problem from Module 5.1. We're going to take a look at example problem number 520. So in example problem 5.20, they tell us that we have a 100-pound weight, and this is suspended by a linear spring with a stiffness given to us as K is equal to 15 pounds per inch, and a viscous dashpot with a damping coefficient given to us as C is equal to 0.10 pound-second per inch. If the system is excited by a harmonic force of amplitude known as F naught is equal to 50 pounds, they want us to determine the steady state amplitude of motion at resonance. So with that information given to us in our problem statement, we can now create our setup page. So on our setup page, you can see up here on the top, I've labeled, this is the problem I'm working on, 5.20. Here is all the given information. Here's what they're asking us to solve for, and down here is our key equation. So from the problem statement, they tell us that we have a weight. So I have a W for my variable is equal to 100 in units of pounds, and this over here is my weight. So I've labeled the variable name, the quantity, the units, and how it relates to my problem. Do the same thing for my spring constant. So K is equal to 15 pounds per inch, and that's my stiffness. C is equal to 0.1 pound seconds per inch, that's my damping coefficient. And F naught is equal to 50 pounds, which is my harmonic force. So I have all of my units. I can double check them right now. Pounds, 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 inches, inches. Okay, we're fine there. So one thing I'm probably going to need as I'm going through these problems is I might need the mass. They give me the weight, but in order to break down my weight into its mass, I know that mass is equal to weight divided by gravity, or weight is equal to mg, mass times acceleration due to gravity. We rearrange that, solve for mass. So now I put in my W over here, which is 100 pounds, and my acceleration due to gravity in those right units is 32.2 feet per second squared. Do this out, and what I end up with is a mass is equal to 3.106 slugs, or 3.106 pound per feet times second squared. So with that information there, that's everything I know. I can clearly come back to this first page to go through all of this, figure out, okay, there's my W, there's my K, there's my C, there's my F naught, there's my mass. The next thing we want to do is figure out what they're asking us. So they're asking us to find the steady state amplitude, right there, of motion at resonance. So we're looking for our U value there at resonance, and we know our resonance is equal to 1. So if we know our resonance is 1, we know we're looking for U, we have all this information here. This is a great time to try to figure out what is our governing equation. What's the key equation we're going to use to solve this? So we look at all the given information, what they're asking us to solve for, come up with this key equation down here. So D of R is equal to U over U naught, which is equal to 1 over the square root of 1 minus R squared squared plus 2 times our damping coefficient times R squared. So next we can begin our solution. So we have our solution page 1 here. We're at resonance, so our R is equal to 1. Now, a couple relationships we may need to reference back to that I write at the top of the page here as I start plugging into my governing equation. I have my omega term is equal to the square root of K over M. So I can get my omega from my known. They gave me my K. I've already solved for my M for my weight, so I can get my omega from that. My H sub R, which is part of my governing equation here, is equal to U over U naught, or in this case here, 1 over 1 minus R squared. And my R in this relationship is my ratio of my omegas here, my omega over my omega sub n. Now we can recall that for steady state magnification factor here, D sub S of R is equal to the magnitude of HR. So we have that relationship there as well. So we want to solve for U over U naught here. We have the relationship 1 over the square root of 1 minus R squared squared plus 2 times my damping coefficient times R quantity squared. So I can plug in, for resonance, my R is equal to 1. So I plug that in here. U over U naught is equal to 1 over the square root of 1 minus 1, which is 0. So this whole term right here goes to 0 there, plus 2 times my damping coefficient times R, which would be a 1 right there as well, squared. Bring this down, reduce, simplify that. U over U naught is equal to 1 divided by the square root of 2. Then we have our zeta term times R quantity squared. So if we reference back to our textbook here to equation 4.14, we can see for our zeta term here, this is equal to C over 2mw. So plug this in. My C was given to me in the problem statement here of 0.1. My M I have there, and I can solve for my omega term from that equation on the previous slide. So M was my weight divided by the acceleration due to gravity, no problem there. I can get my omega here now, so omega is equal to the square root of k over m. Plug in my value for k from the problem statement, plug in my value for m that I solve for from my weight factor, and I can get my omega term here of 7.61 radians per second. So that can plug back up in here into my omega term right there in order to solve for my zeta. So continue on there. There's my general equation from the previous slide there. 0.1 divided by 2 m omega. I have my m given to me in the problem statement. I rewrite it out here. I have my omega that I've just solved for. I can plug those in there. Now I can get my zeta term here is equal to 0.1 divided by 2 times 0.2578 times 7.61. So again, that is my mass and my omega term that I just solved for. So now I have a numeric value here for zeta term is equal to 0.0254. So I can take this and plug back into this dr equation now. So u over u naught is equal to 1 over the square root of 2 times the zeta term times r squared. Well, this is a 1 value there, and now I have a numeric value of 0.0254 for that there. So u over u naught is equal to 1 over now the square root of 2 times, put my 1 in there, squared there, plug in now here for my zeta term right there, and I have 1 over the square root of 2 times 0.0254 times 1, quantity squared. So my u over my u naught then becomes 19.685. So with that value of u over u naught is equal to 19.685, I now have u can be separated out. If I rearrange this, u is equal to u naught times that 19.685, where, if we recall now, we have an equation relationship for our u naught here, F naught over K. So my F naught's given to me as the problem statement is 500 pounds. My K is given to me as 15 pounds per inch. So I can plug straight in there, and now I can get a value for u naught right there. In inches, if I have my u naught and I want to solve for u, I can then rearrange this top equation up here down into this guy here and plug in for my u naught with this value right there. Plug that guy into that there. And what we end up with now is u is equal to 3.33 times my 19.685. So u is equal to 65.61 inches. That's my final answer for my amplitude.